Hello, my dear students, and welcome to our lecture coverage of Chapter 5, titled Thermochemistry, for Brown and LeMay's, I should say Brown and LeMay et al.'s. I first encountered your textbook many years ago as Brown and LeMay, but they've added additional authors which have greatly enhanced its readability and teaching effectiveness. But for Chapter 5, this is a discussion over thermodynamics, thermochemistry, as you can see here for the title of the chapter. And what else? It's a very long and somewhat detailed chapter with a lot of details we'll use later in second semester chemistry, and you'll especially want to pay attention to if you're interested in physical chemistry or biochemistry and or biophysics. Technically, I am a biochemist, bioorganic chemist, biophysicist, and we discuss energy changes quite frequently as it relates to life. But I think we can, let me just phrase it this way. My plan is to quickly move through this chapter and assign a few typical test questions so that we can move on to Chapter 6 with, my problem is it doesn't automatically relate and build until later. And it also, this chapter is a bit of a mishmash. I like having all the authors, many hands make light work, but there's also another saying that too many cooks spoil the broth. The chapter also starts discussing aspects of gas pressure, which is in a subsequent chapter. I want to say Chapter 8. My point is, let's get through this and try the quick homework before you quickly move on to our discussion of more detail of the electronic structure of the atom and how that relates to periodicity and periodic properties in the next two chapters, which are essential to our coverage here in general chemistry. So, thermodynamics is the study of energy, and I guess its transformations, and we'll talk about that. And thermochemistry, of course, is how thermodynamics relates to chemistry, specifically the relationships between chemical reactions and energy changes. So what is energy? It's the ability to do work or transfer heat. And we'll look at a relationship between work and heat when we talk about enthalpy and internal energy and some topics as we move into this chapter. If you cause an object to move, it's called work, and you'll know that later work is equal to force times distance. You may remember that from physics or physical science or from high school physical science. And energy used to cause the temperature of an object to rise is termed heat. Okay, so we're going to discuss those energy changes in chemical reactions with an idea toward understanding chemical reactions and the nature of matter a little better. So, there's all kinds of energy. I have a quick question in the assignment asking you to classify energy. Kinetic energy is the energy of movement. You may or may not remember it's equal to 1/2 mv squared, where that kinetic energy, you may have written it as a capital KE, is excuse the call in the background, but let me see if I can do this and use my, you may have learned it as KE, kinetic energy, when you took physical science, but your book calls it energy, with a subscript K for kinetic. Very dangerous subscript in chemistry, since that usually stands for constant. But the mass is m, little m, and the velocity in our equation is v, and the square of the velocity times the mass, 1/2 mv squared, is equal to your kinetic energy. And then you have potential energy, which is energy that relates to an object's position. You may have heard of your potential energy for this bicycle rider in the previous example as mgh, okay? That's its mass times acceleration due to gravity, which is relatively constant here on Earth, times the height, how high that hill that bicycle rider was. In chemistry, we worry more about electrostatic potential energy, and once again, there is an important measure of distance, this time not how high, but how close two charged particles and their charge are. The Q1 and Q2 referring to the charge, okay? So, potential energy is the object and the energy an object possesses by virtue of its position or chemical composition as well, because we'll have chemical potential energy that I guess also I could argue relates to this electrostatic potential energy. You know that if you take two like charges and put them together, it takes energy to do it. Because as you push, for example, two north poles of a magnet together, they won't go together unless you put energy into the system. And you also know that if you have opposite charges that attract, a north and a south pole in a magnet, or a positive and negative charge in our chemical particles, that they will naturally be pulled together, and it takes energy to keep them apart. So, you know energy is being expended. Now, our unit of energy, and this is something I do want you to remember, in chemistry is a joule. Myself being a biochemist, I frequently use calories. It's the calorie is defined as the amount of energy required to increase 1 gram of water 1 degree Kelvin or Celsius. That dimension is the same in Kelvin and Celsius. And it's used a lot. Now, when you talk about calories in food, those are actually kilocalories, or 1,000 of these calories, okay? But the joule is kilograms meter squared per second squared. We won't discuss deriving that. You do that in physical chemistry or just plain physics. But you will hear me talk about joules, and we can convert these back and forth, because a calorie is about 1/4 of a joule. There are 4.184 joules in a calorie. Now, you may have heard these definitions before. We have our system that we're studying, and everything else that's not part of our system is our surroundings. We may separate our system from our surroundings with insulation, so that there is no transfer of heat in and out of our system, or no transfer of heat from the surroundings to the system, or no transfer of heat from the systems to the surroundings. And that heat energy means we can focus on the energy in our system. You also see here, this is set up with a piston that itself may move if we have volume changes, especially with gases. Those of you who've had physics or know, that would be called an adiabatic system, where no heat is transferred between the system and the surroundings, but we can't have energy come and go as work, because remember, work is force times distance, and we moved something. We have a distance. Now, this is getting pretty heavy, but what we really want to be talking about really is our heat energy. So, energy is useful because it can move an object over some distance. As I said, work is force times distance. That's our formal definition of work. We all have our practical definitions of it. But what we are most concerned with is heat and transfer of heat. That is a transfer of energy, make no doubt about it. That thermal energy or heat only flows from warmer objects to cooler objects. If I may have an aside for 1 minute, heat does not flow up, okay? You hear that a lot, that heat rises. Heat doesn't rise. Heat only flows from warmer objects to cooler objects. That's the only direction it can go, from warmer to cooler. Now, if you have warm air, you will find that as you add energy to that air, make it warmer, you increase the thermal motion of the particles, and for a variety of, I won't say a variety of reasons, but with a variety of effects stemming from that, you will see that air rise because it becomes less dense. And it carries that thermal energy with it. So in practical terms, the heat rises, but in less practical terms, not in practical, but in pure scientific terms, heat does not rise. It flows from warm to cool. Now, if you warm something up, you will cause it to expand most of the time, with notable exceptions, water. But that object will expand, whether it's a piece of metal or 90% of the time we're talking about a fluid, and specifically a gas. It will expand and it will rise. Hot liquids are less dense than cold liquids, and they come to the top of the container, whether the container is a great sea or a beaker in the lab. So heat flows. And energy, as you know, can be converted from one type to another. You take that chemical potential energy in your battery, and using mechanical energy, you turn a key is turned, that what? Opens up a circuit so that electrical energy can flow as a result of that chemical interaction to the engine that will subsequently pump mechanically the gasoline and the air and mix them together and burn them, causing them to expand and push a piston, which pushes the crankshaft, which pushes the flywheel, which pushes the transmission, which pushes through the differential to the axles and turns the wheels. So when you just get in your car and drive, you're looking and using and exploiting, perhaps without understanding, thermal energy, chemical potential energy, electrical energy, thermal energy, quite obviously, heat energy, that engine gets hot, and of course mechanical energy. so that you can go where you want to go in your car. So thank goodness energy can be converted from one form to another. Now right here, they're just saying I have, by virtue of my position, my height, potential energy, and I can convert it to kinetic energy. And of course, your car would have kinetic energy to get you where you're going. Sitting in your driveway, it's full of potential energy. All different kinds, I guess, if it sits at the top of a hill as well. So let's talk about our first law of thermodynamics. You've heard this stated various ways. The total energy of the universe is constant. Energy can neither be created nor destroyed. And so it's a law that we must obey. Now, the internal energy of a system, and we're talking chemical systems, and we're really talking about and continuing to visit those chemical reactions we've been talking about in the previous 2 chapters. But the internal energy of a system is the sum of all the kinetic and potential energies of that system. If I can go back, I forget how to do it here. Shall I go back? Yes. This person has so much potential energy, and then when they meet this slope, and if it's a frictionless slope and all things are under theoretical conditions that we don't really encounter in real life, we'll convert that potential energy to kinetic energy. But on the way down, depending on where they are on the hill, they'll have less and less potential energy, and they'll start going faster and faster and faster and have, as they go downhill, more and more kinetic energy. So the potential energy is decreasing, because obviously a bicycle at this level doesn't have as much potential as a bicycle at this level. And as that rider or bicycle is released, we do this in the lab. We release a little cart, a Hall's cart or something, from a ramp, and we see it go faster. The higher the ramp or the steeper the ramp, the more kinetic energy we are able to get out of that potential energy. We can get more if we reduce the friction and other forces acting on that besides gravity, our mgh, or height, and this is 1/2 mv squared. Of course, you see this mass is important in every case, but we're interconverting them, and that's what they're talking about, is converting different forms of energy. Initially, just for introduction, the interconversion of potential and kinetic energy. But when we talk about this internal energy of a system, we have our initial and final states. In some cases, energy may be released and lost to the surroundings, or to get to our final state, we may need to put energy in and transfer energy from the surroundings to our system for a reaction to occur. These are the 2 types of reactions I would like you to know about. The sum of all the kinetic and potential energies of all the components of this system is the internal energy, and it's the final minus the initial after a reaction or a change occurs. Let's think chemical reaction, but this could also refer to, for example, pushing a piston or moving something, and we have a beginning and ending state. In this case, we have hydrogen and oxygen gas, and at a much lower energy, these have a great deal of potential energy, And after we react them and have formed water, it's at a much lower energy state, and as a consequence, we release lots of energy. In fact, explosively so when you do this reaction. So, if the change in energy, let's go back, the final minus the initial is less than zero. In other words, it's negative, okay? I had to have absorbed energy from my surroundings, and energy came into the reaction, and that is called an endergonic reaction, okay? And the energy change is endergonic, okay? This one. We had to put energy in. If that change in energy, in other words, final minus initial, is less than zero or negative, okay, the final is less than the initial. Okay, let me make sure I say this right. The final energy is less than the initial. The final state here has less energy than I initially had. Where'd the energy go? It went out of the system and into the surroundings. It exited the system. And that's an exergonic reaction. It released, we know this, it released heat. Okay, we burned something, or we oxidized something with the release of energy, but that chemical reaction released energy, or that process released energy. Our final energy state is much less than our initial. Where'd the energy go? Well, it has to go somewhere. It can neither be created nor destroyed, correct? That's our first law. We always have to follow that. So if our final energy is less than our initial, we lost some energy. And we lost it most typically in a chemical reaction as heat. I like to always say heat and light because I love, in biochemistry, reactions that are chemiluminescent or bioluminescent. Anyway, our change in internal energy changes when we lose heat, which we are going to designate Q, or when we do work. We expand the bag. It doesn't really show work coming, it's just doing arrows. Or we push and expand our system causes a piston to move, for example. So energy, remember these are different forms, thermal energy and mechanical energy. Work is force times distance, and we applied a force across a distance to move something. We did some work. So we are going to sum our internal energy in a system as the amount of heat and the amount of work that occurs. So when we have our equation, we need to pay attention to the signs. For heat, if it's positive, it means the system gains heat. I have added heat to the system. If it's negative, it means my system loses heat or gives off heat, releases heat. Now, most cases that means exergonic, okay? When work is done on a system, we're calling that positive. A lot of people in physics and physical chemistry tend to get this mixed up, but we don't have to worry about it too much here in introductory college freshman chemistry first semester, okay? But this definition is important, and you will see it again if you go on in the chemical sciences. Work done on a system is positive. Work done by the system is negative because you put that work outside. You did that work. You released that energy. You lost some energy, so it is negative. That's just the way I look at it. I'm not sure that's that a physicist would agree with that sort of reasoning. And for our change in internal energy, if when we add up our Q plus W, if it's positive, it means a net gain of energy by the system. Now, this is my true, I'm putting energy into the system, endergonic reaction, because you may not have noticed a heat difference if if the work difference swamps it, overwhelms it. Whether we're talking endergonic or exergonic, you have to consider both. But people's, I guess, problem is considering just the thermal energy or heat, Q, gained and lost. But when we add those two together, if we have a net loss of energy by the system, we release thermal energy, transfer it to our surroundings, or we kind of release work. We do some work and give it, do it. Then we are truly exergonic. To talk about and ignore the work and talk about the temperature, when heat is absorbed, it's endothermic. You can observe an endothermic reaction very frequent in the lab. If we were in a lab, and that's why I'm not crazy about teaching chemistry online, because I'm always doing demos and always saying, okay, let's look at this. But you've seen this. Get a cold pack. And it's not a true chemical reaction so much as a phase change, okay? But you have an endothermic reaction that absorbs heat from the surrounding. It doesn't release heat, it absorbs it. And cools things down, feels cool to the touch, okay? I don't know what they're probably dissolving mag sulfate in water or something there. I don't know what salts they use. I know they use, I want to say, some ammonium salts in those cold packs. I always keep one or two handy so I can demonstrate them, and I have one where you can view the reaction because it's in clear plastic and reusable. But we will skip this. An exothermic process, this is an extremely exothermic, rapid process. Talk about reaction rates, kinetics next semester. But it's releasing heat, okay? The example I like to use that complements my previous example is an exothermic reaction with the heat packs, okay? It's a slow oxidation or rusting of iron in the presence of oxygen. That's an exothermic reaction that releases heat, and you can use it to keep your hands warm. So, a state function is one in which, and this is important for us this time, at this time, state function is one in which the path is not important. Only the beginning and final state are important. So, excuse the interruption here. I have this example, which is, if, from the book, of course, this water at room temperature, 25 degrees Celsius, 50 grams of water, has the same internal energy whether it started out as boiling water that cooled or whether it started out as 50 grams of ice that warmed, okay? So this released some of that energy to reach this energy state, and this absorbed energy from the surroundings to reach this energy state. But what matters, is this state, not how it reached there. Okay? There's no difference in this water whether it came from hot water or cold water. And you see some people making some crazy statements on the internet about who don't understand these things. I don't want to go into politics or get on my soapbox. So, internal energy is a state function, and it depends only on your initial and final, the change in energy in a system depends only on the initial and final states of that system, not the path by which it takes. As a biochemist, studying things like glycolysis, we take sugar, glucose, and through glycolysis and respiration, we turn it into CO2 and water, right? We basically burn it with some oxygen. And this releases the same amount of energy whether I touch a match to it or whether I run it through 20 or so enzymatic steps, small steps that get me to the same state. And the amount of energy released is the same, no matter the path, because it depends on the beginning state, glucose plus oxygen, and the final state, carbon dioxide and water. And indeed, sometimes I can exploit those small steps to capture energy, transfer energy, have a reaction proceed that might not normally because the following reaction will. So my point is this is a long, circuitous, complex path in the human body from glucose to carbon dioxide and water. But if you have glucose in a test tube and oxygen, you can light a match to it and it will burn. And burn very simply, but the amount of energy released by a given amount of glucose in excess of oxygen will be the same, because it depends only on the fact that it's glucose and the fact that we're making carbon dioxide and water. So, Q and W are not state functions. When I burn that glucose with a match, almost all of the energy is released as heat and light. When I metabolize glucose, I get the same amount of energy change, but I also transfer that and capture some of it. Your book uses the example of a heater element, a toaster element, for example, a resistance. Of course, there's resistance in this fan too, and a fan. Okay? In the heating element, all of that change in energy, my battery goes from a charged state to a discharged state, and because of a series of chemical reactions, but it releases that chemical energy as heat, 100% as heat. In the fan gets hot, warms up, the motor warms up, there's resistance in the fan, and there is some heat released to the surroundings. But there's also a lot of work moving that air around and moving that fan blade that subsequently moves the air around. And overall, the battery started out charged, it ended up discharged, and it didn't matter whether it went through this circuit or that circuit. The beginning and ending state are the same. That's just a way of emphasizing this is a state function. As I've already told you, and I want to start going quickly through this because I just want to give you a few conceptual problems and questions and then move on to our, like I say, what I won't say I'm working important, but our, at this point, more essential topics in the next two chapters. Well, now, as I said, work is force times distance, and one way we measure work in chemistry and in physics labs is by movement of a piston, whether we move it down or our system expands and moves our piston up. That is the kind of work we usually are measuring. Like I said, we'll get to gases in a few more chapters. Here's a classic example. You have a flask full of hydrochloric acid, and one of my favorite ways of producing hydrogen gas is to add a metal, a cheap metal, that's above hydrogen on the activity series so that it is replaced. We make zinc chloride, and they don't have to show the spectator ions in this reaction, but we make zinc chloride from our metallic zinc and our hydrochloric acid. And the main thing is we make hydrogen gas, which we can trap and collect, and which we're working at constant pressure, then we will have a change in volume. So work here is, indicated by a change in volume. Now, let's talk about enthalpy, and it's the internal energy of a system that's equal to well, what I would rather do is rearrange that equation, but this third section of your chapter talks about enthalpy, the amount of heat absorbed or released by a chemical reaction when we're under constant pressure. And that process, not that process, but this equation, it relates energy and work, okay? So, our change in enthalpy is equal to our change in energy plus our change in work. And here it is. And we measure work as a change in volume, okay? So, Q is our heat energy, W is our work, and of course our work is our change in volume. It's our change in volume if we keep our pressure constant, but P delta V. We can substitute these and see that if we have our enthalpy is equal to our change in energy plus our change in work, and our change in energy is our heat plus our work, okay? The heat energy plus the work energy, then we substitute this for our delta E, and this is how we defined our work in our system, so it's another work. So delta H, change in enthalpy, at constant pressure is equal to our change in our heat. Okay? So, we may sometimes, I want to say, your book has it and calls it Q with a subscript P, which is a reminder that you're working on a special case, at least where a physicist is concerned, where pressures are constant. So, if delta H is positive, okay, it's endothermic. Okay, if we absorb heat, if we add heat, it's positive. If delta H is negative, the change in energy is negative. A process is exothermic. Okay, If delta H is negative, the process is exothermic. It just means that heat is being released. See the term there? Heat loss. Okay? What we want to do is enthalpy reaction. Now I'm going to go through this very quickly because it's fairly complex and it's not difficult in a comprehension sense. It's just difficult in that it can be a very tedious, stepwise process that I think a lot of students find it common to make simple errors in. But if you're careful, I hope I can explain what we just talked about with state functions by considering the beginning and ending state and not the path. And so we can exploit previous people's work to create a path to calculate the energy inherent in a chemical or the energy gained or absorbed by a chemical reaction. So the change in enthalpy is a change in enthalpy of the products minus a change in enthalpy of the reactants. You might call this the beginning minus the final state, okay? Here I have methane as I was taught it, plus 2 oxygen, 4 oxygen atoms, reacts to form carbon dioxide and water. And it releases 890 kilojoules. And the change in enthalpy going the other direction, also called the enthalpy of formation, heat formation, is 890 kilojoules, but must be put in so it has a positive sign. Now, it's called the enthalpy of reaction or heat of reaction. Here's hydrogen plus oxygen going to water. It flames and makes a nice explosion, nice laboratory demo. If you don't do too much at one time and you keep it safe. And it's a highly exothermic reaction. It's an extensive property. That means, if you remember your basics, that it depends on the amount and not the nature of the substances present. The delta H for reaction in forward direction is equal in size but opposite in sign to the delta H for the reverse reaction. We saw that here. And the delta H, or the enthalpy, or change in enthalpy for a reaction, or the heat of reaction, depends on the states of the products and the state of the reactants. It's a state function. It doesn't depend on the path, okay, or the number of steps. We can observe change in enthalpy in the lab using a simple device termed a calorimeter. It can be as simple as a styrofoam cup that provides us insulation between our surroundings and our system, and a thermometer that measures the temperature before and after. We've put our thermometer in here. It may be reading right there. And then we allow a reaction to occur and we measure the temperature change, going up or down, depending on the reaction. And measure the greatest change. Knowing amounts here, we can do some quick reactions. But you really need to be in a lab. I like to use a thermocouple and a data collector to collect that data so we can catch the greatest change possible. Heat capacity. The amount of energy required to raise the temperature of a substance 1 degree is its heat capacity, usually given for 1 mole. Water This is 1 gram. This is joules per gram. But there are specific heats. These are, it says, usually given for 1 mole. All of these are given for 1 gram. The joules required to change 1 gram, 1 degree Kelvin or 1 degree C. And you can see water has a very high specific heat. If you take something like steel, it doesn't take much to heat it up or cool it down or have it heat something else. And it has very low specific heat. This is an important biological property of water, by the way, too, and has important consequences you can learn about in biology. So specific heat, nobody really says specific heat capacity, but specific heat, amount of energy required to raise the temperature of a given amount of substance, a given number of degrees, in this case 1 gram, 1 degree Celsius. Water, to go 1 degree, takes 1 calorie or 4.184 joules. Specific heat is easy to measure. I'm not even going to give you any problems. I will just tell you it's equal to the heat transferred. That's the energy Q. So you can calculate Q if you know your mass and your change in temperature, and you have your specific heat, which you can look up in a table for most substances. Just quickly, constant pressure calorimetry. You carry out reactions at atmospheric pressure. You can, if you're doing solution chemistry, we know the specific heat for water, and we can calculate the change in energy. Remember, this equation is useful, but it's useful because I can find Q. Because I can look up my specific heat, I can measure my temperature change, and I can measure my mass in the laboratory, and that will give me the energy. Now, if you want a reaction to be carried out where it's in a sealed container, basically, if you have a change in pressure, you've made a bomb, so this is called bomb calorimetry. You can put a thermometer into your system, tightly seal the cap on an insulated container. You can mix it up and mix reactants or add current and have a reaction occur that will instantly give you the heat of the reaction. Okay? The volume, like it says, is constant. Nothing can change. If gases are released, it builds up pressure in here, and you're measuring your change in internal energy. The difference, we're not going to go into that anymore. Let's move on to Hess's law, which is very important for us because it reiterates several things I've talked about, and that is, with Hess's law, I want you to remember that enthalpy is a state function. So the enthalpy change, delta H, associated with any chemical process, depends only on the amount of matter and the initial and final states, not the path. Okay? And there are many published delta H values. I've already talked about this. If you carry out in a series of steps, the overall reaction will be the sum of the steps. Okay, it doesn't matter how I go from methane to carbon dioxide and water, whether I go to CO, carbon monoxide and water and oxygen, and then to these, or I think some people want to just consider carbon and hydrogen and oxygen separately, and then use the heats of formation to do these, you can do those kinds of things. I will show you how you do that. If a reaction is carried out in a series of steps, the enthalpy change, delta H, for the reaction will be equal to the sum of all of the individual steps. And that is independent of the number of steps. And I just am going to show you this one example from the book. We use these standard tables of enthalpies, or tables of standard enthalpies, and enthalpy of formation. We sometimes call it delta F0, which means not at 0 degrees, but at 25 degrees and 1 atmosphere of pressure. And the biochemists sometimes may do it at something other than room temperature, like 37, and they may call it 0 prime. But all these means is that the conditions are defined, and people have, doing calorimetry, measured these, or done what we're doing, which is calculate it by considering the steps involved. So here's propane, C3H8. We burn it with oxygen and we make carbon dioxide and water. Now, they're saying let's visualize this as occurring in 3 steps. Okay? So they want to break this down completely to graphite, pure carbon, or diamond, I guess, but not really, and hydrogen gas, and then combine it with the oxygen. And when they do that, this 5 oxygen, okay, then they're going to make carbon dioxide, and that leaves us with hydrogen and oxygen, and then we convert our hydrogen and oxygen to H2O. So you see, instead of burning this and going right down there to carbon dioxide and water, we may not have the information we need. It's right there, but in a reaction, we may not have that reaction. So we can play some games by rearrangement and find through some other pathway what our heat of formation or our change in enthalpy for this reaction is, given the heat of formation of known compounds, known heats of formation of known compounds. So we want to calculate our change in enthalpy, and we have these values, okay, and we needed this value to put them in there. And I think you can see we have 3 steps: the formation of the graphite and the hydrogen, and then the formation of the CO2, and then the formation of the water from the hydrogen when we combine the carbon with the oxygen and then the hydrogen with the oxygen. And when we do that, if you look at these bold values, we have minus 1143 kilojoules, that's 1,000 joules, minus 1181 kilojoules, and we can sum those together to get this energy difference. But don't forget, we didn't really start here to go there. We started here. So this will have to be considered as well. And if you do the math and you add these reactions up and you look at what cancels out, graphite and graphite, you know, on the left side of my arrow, I've got one of these, and I don't have these because I can subtract those out, and I have 3 plus 2 or 5 oxygen. And on this side, I've got 3 carbon dioxide these hydrogens cancel each other out, and these carbons cancel each other out, and 4 water. So they just did it. So Hess's law says this change in enthalpy is the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of reactants. And these are your stoichiometric coefficients. In other words, back in this one, 1 for the propane, 5 for the oxygen, 3 for the CO2, and 4 for the water. So, going from the table, we look up our propane, we look up our what? Oxygen. We look up, or well, they also gave it to us here, but we see using these values for example, for oxygen, I need a 5. Now, what's the enthalpy of formation for an element? It's always 0. Just FYI. So, that's a really long, involved process to get to this answer. Remember I said you sum these, and that gives you this value. And then we have to consider this, but we added it in, so we minus a minus there, as they said. And that's your overall change in reaction. And this calculation from this path should equal this, 2219.9 and 2220. Let's talk about a little bit of, I guess, biochemistry, because one of the things we're interested in is applying this to things we feel most interested in. I don't want to tout biochemistry too much, but we're interested in ourselves and our bodies. And carbohydrates, sugars, have 17 kilojoules per gram, but let's do calories per gram. For calories, big C, that's actually a kilocalorie per gram. 4.184 is a conversion factor. So a little over 4 times 4 is 17. But let's talk calories, because this is what you see on the back of the box. You can see that fat on a mass per mass basis has over double the calories of either carbohydrates or proteins. Now, these per gram have far less than just pure fat or pure protein or pure sugar in general, because they include water and a mixture of fats, carbohydrates, and proteins. So you see values that you can see high density, high calorie foods like fudge versus lower density, low calorie foods like an apple. And college students, of course, are interested in, yes, does beer have calories? Depends on the beer. Okay? Now, fuels. This is, I don't know what year I got this from, your book, but it said renewables are 7%. Nowadays, last I looked up, about 20% of U.S. renewable energy was, about 20% of U.S. energy consumption was renewable. That included only about 12% of that, so 12% of 20%, or just 2 or 3% was solar. 40% of that was biomass, like gasohol. But about a third of that 20 or 7% of our total was actually wind. A significant part, but wind has overtaken hydroelectric now. So, just something to consider. So, anyway, the shame is we have all that solar energy there for free. So, our renewables are now about 20%, and of those renewables, last number I saw for last year was about 13% solar. Oops. And that is it. So I will say look for the assignment and look for the next chapter coming even tomorrow. I want to get these posted and get going. So do your assignments. Please catch up. I have a lot of people who haven't done the past assignments. I don't know if this will be posted before or after spring break. But either way, please catch up. Please do these quickly to move on to our very important material, starting with our next chapter. Goodbye now.